let us discuss electric potential. So what is electric potential? Now electric potential due to some source of charge, okay, there has to be a charge which is producing electric potential, is defined as the work done by external agent in taking the unit positive charge from a reference point. This reference point is generally taken as infinity. So we'll say it is the work done per unit charge to bring that charge from infinity to that particular point. This is how we define electric potential at a particular point. Now let us say that we have done the W work. If capital W is the work done by external agent in bringing a positive charge Q naught. Q naught is our positive charge. Then what is the work done per unit charge? W divided by Q naught. Total work divided by total charge. This and V is the potential at that point. Then V is work done per unit charge. So this is the formula for calculating potential at particular point. This external work is nothing but infinity to this particular point A, and this is the potential at that point A. Now, if we are talking about the work done by electric field, so see, there is a condition. When you bring that point charge from infinity to all the way up to that particular point A, let us call that particular point is A. We are bringing our charge from infinity to all the way up to this point, and potential over here is A. We are doing W work. So work done by external force is W external and work done by electric field is WE. Then these two work are basically negative of each other, because there is a condition that you have to keep the kinetic energy same, and if you are keeping the kinetic energy same, means the total work done has to be 0. Or other condition, you can say the acceleration is 0 and hence velocity will not increase decrease. So if acceleration is 0, then forces has to be balanced. So if we are applying the F external force and field is applying FE, then these two forces must be always equal and opposite, and hence their work are also opposite in nature. So work done by external force is same as negative of the work done by electric field. So it is also defined as the potential at any particular point is work done by external force per unit charge, or we can say negative of work done by electric field per unit charge. So this is how potential at a particular point is defined. Both the work are from infinity to that particular point. Now let us discuss some of the properties of our electric potential. So first property is potential is a scalar quantity. It is work done per unit charge. So as work is a scalar quantity, potential is also a scalar quantity, and like work, it might be positive, might be negative, or might be 0 as well, depends on the work. If work is negative, then potential at a particular point is also negative. Work done by external force I am talking about. Work done by field is basically the opposite of that. So if work done by external field itself is negative, then your potential at a particular point is going to be positive. Second property is SI unit. So as we have already discussed, it is work done per unit charge. So work is calculated in joule and charge is basically coulomb. So SI unit is basically joule per coulomb, and joule per coulomb is known as volt. So we'll say 1 volt is 1 joule per coulomb. So this is our SI unit of the potential. Next is the dimension. If we are writing the dimensional formula, then it is joule per coulomb. And now we know that coulomb is charge, so it is basically ampere second. We know that Q is equal to IT, the current into time. Current is equal to charge upon time. So ampere second is coulomb. And what about joule? Joule is work. So Newton meter, that is our work. And what is Newton? Kg meter per second square. Now if you see, there is kg meter square upon second cube ampere. So it is m1 length 2 time -3 and ampere, that is current raised to power -1. So this is our dimensional formula for 1 volt, or we can say potential, dimensional formula for potential. Next property is electric potential at a point is also defined as negative of the work done by electric field, right? So we have already discussed that work done by electric field is basically negative of work done by external field, and potential is defined as work done by external force per unit charge, and that is negative of work done by electric field per unit charge. So it is also defined that way. So that we have already discussed while writing the original formula. Now next property is potential decreases in the direction of electric field. So see, let us say that this is a point charge capital Q. The electric field lines are going away from it because this is positively charged. Now, if I have to bring another charge from here to all the way up to this point A, then I will do some work which is against that electric field which this Q charge is producing. So I will do some positive work because I am applying my force against the, so this is my F external which is against the force of the electric field, and this will be some positive work. And if I have to bring it all the way up to here, then I have to do more work. So more work per unit charge means the potential of B must be greater than potential of A. And if we are moving in the direction of electric field line, that is from B to A, and as you can see potential is decreasing. So we can say potential decreases in the direction of electric field and it increases in the direction of opposite to that of electric field. Now next is potential difference. So what is potential difference? Potential difference between 2 point charges is equal to the minimum work done or work done in moving a unit positive test charge from one point to other. Previously we defined absolute potential, and for defining absolute potential we needed to take a reference point, and that reference point was infinity. So now previously we were bringing it from infinity to that point. Now we are moving from one point A to another point B. And now work done per unit charge, moving it from A to B, is going to give me potential difference between point A and B, or we can say the potential difference between VB and VA is work done per unit charge from A to B. So final potential, it is basically the potential difference. So work, and this is by external. So if we rewrite this equation, then we can also go for that WAB is nothing but Q naught times this and Q naught, and what is this VB minus VA? We were starting from A and going all the way up to B. So we can write that as delta V. So Q naught delta V is work done, but this work done is work done by external force. Next is, what if we are talking about the work done by electric field? So if W is the work done by electric field, then basically we can say that the work done by electric field is negative of the work done by external force. So instead of this, we will write negative of work done by the field, and from there we get work done by electric field is Q naught. This goes here and it is delta V, and there is this negative sign. So the work done by electric field is nothing but minus Q naught delta V. So remember, if we are talking about work done by electric field, it is minus Q naught delta V, and delta V is like V final minus V initial, or potential of the final point minus potential of the initial point, that is the potential difference. Now let us discuss some property of the potential difference. So first property is the difference of potential between 2 points is called the potential difference. Its basics, basically the difference of two potential is the potential difference. And now next is the potential difference is also a scalar quantity. See, potential is a scalar quantity and their difference is also going to be a scalar quantity. And what about its unit? Unit is also going to be volt. The difference of some volt minus some other volt is going to give you some other volt. So basically if is a 5 volt minus 7 volt, then that will give us minus 2 volt. So the difference of two potential will also be calculated in volts only. If V and VB are the potential difference, potentials of two particular point A and B, then work done by external agent is nothing but Q delta V, we have already discussed. And if we talk about work done by electric field, then that is minus Q delta V. So delta V is nothing but VB minus VA. So this is final minus initial, that is VB minus VA, and there is this negative. So when this negative goes, we get VA minus VB. So rather than remembering this, I would suggest that you remember that work done by external field, external force is Q delta V, while the work done by electric field itself is nothing but minus Q delta V. Now next comes potential difference between 2 points is independent of our reference point. Like the gravitational potential difference is also independent of the reference point. It doesn't matter whether you take the reference point at a limited distance or you take the reference point at infinity. When you calculate the difference, then basically you are finding this work done. So it is this work done which matters. Now you are bringing that from infinity to this point and infinity to this particular point, or you are bringing from this point to this point and this point to this point. It does not matter. The difference is always going to be same. So it is independent of your reference point taken. Now let us discuss a question. So this question says that 1 microcoulomb charge is shifted from A to B, and it is found that the work done by external force is 40 microjoule in doing so. So we need to find the potential difference. So we are moving from A to B. So work done in moving from A to B by external force is nothing but Q delta V. So Q into final minus initial. So this is 40 microjoule. Charge itself is 1 microcoulomb and it is VB minus VA. Is like we are moving from A to B, so final minus initial, and micro is gone, so we will get VB minus VA to be 40 volts. Now micro and micro is gone, joule per coulomb is volt, and now we will say what is question asking? Question is asking VA minus VB. So VA minus VB is going to be minus 40 volt because VB minus VA is 40 volt. VA minus VB is going to be minus 40 volt. That is going to be our answer. Next is the relationship between electric field and the electric potential. So if we go about the original definition of potential, it is defined as potential is nothing but negative of work done by electric field per unit charge. Now what is the work done? Work done is basically force into displacement. So I will say let the small work done be dW and small potential difference be dV. And now I get Q dV is equal to negative of dW. And what is the small work done? Work done is nothing but F dot dr. And now here this is nothing but force by the electric field. What is the formula for force due to electric field on a charge Q? It is basically QE. So this can be written as Q dV is equal to minus Q E dot dr. So Q is gone and we get dV is equal to minus E dot dr. So this is the relationship between potential and electric field. If we make the E, if we want to get a formula for E, E is nothing but minus of dV by dr. So it is electric field is the potential gradient, but this is not the vector formula. For vector formula we needed to do something else. So first is if we have to get the electric integration dV, then integration of dV is nothing but integration of minus integration of E dot dr, and that is which is written over here, that integration dV is nothing but minus integration E dot dr. And if we have to get E, then individually if we want to talk the electric field along x-axis, then what have we discussed? The E is nothing but dV by dr. So if that r is taken as x, so dV by dx, negative of dV by dx, given that y and z are constant, that will give you x component of the electric field. This is a vector quantity and this is a v, is a scalar quantity. So we will assume that y and z are constant and then we differentiate with respect to x, we get the x component. Similarly, if we differentiate with respect to y and assuming x and z to be a constant, then we get the y component. To get the z component, we differentiate with z, negative of the potential gradient, and y and x can be assumed to be a constant. So this is known as partial differentiation. So this is the formula for electric field. So this is nothing but, this is negative of dV by dx, assuming that y and z are constants. So this is called partial differentiation. So there was a formula for force. So force is nothing but minus del u by del x. The force is negative of differentiation of potential energy with respect to x, y and z, and that was also partial differentiation. Similarly, the electric field is also partial differentiation of potential and negative of that with respect to x, y and z, one by one. So when you differentiate with x, you get I component. When you differentiate with respect to y, you get x or j component, and when you differentiate with z, you get k component. Those are x, y and z component respectively. Now let us discuss electric potential due to a point charge. So we have a point charge over here. So this is a point charge plus Q, and now we have to find the potential at this point P, which is situated at R distance. So what I am going to do is, I am going to take a distance x, and now I am basically moving a charge from infinity to this particular point P. So how will I define? I will say that potential is nothing but, it is defined as work done per unit charge. So I am taking a Q charge. Let us take this as Q naught. So I am taking Q charge over here, and I am moving that charge all the way up to P from infinity. So let us say our charge is at a distance x, and now I am moving it in this direction by dx. So here the work done will be what? The force into displacement. So force is Q into electric field at x, and dx is the displacement. Here, as you can see, your x is continuously decreasing. So your dx is negative because the dx is change in x, and which is negative. To make it positive, I am putting a minus sign over there. Divide by q. So this is gone, and it is integration of ex and dx. So I have to integrate this to get the potential, and the x is changing from all the way from infinity to this r. What about E at x? Electric field at x due to a point charge is given by kq by r square. So this is minus kq by r square, which is x square dx. And integration happens from infinity to particular distance r. So what is the integration of that? So k q naught is as it is. Integration of 1 by x square is minus 1 by x. And now there is a minus sign, so I am making it positive, and it is infinity to r. That gives me k q naught 1 by r minus 1 by infinity. 1 by infinity is 0. So this is k q naught by r. So we say that potential due to a point charge at r distance is given by kq by r, where q is nothing but the charge and r is nothing but the distance of point, where like distance of point from the charge. So this is the formula kq by r. Now let us discuss electric potential due to a given distribution of charge. So there are two possible types of distribution. One is continuous charge distribution. One is discrete charge distribution. So if the potential at any point due to a group of point charges is nothing but algebraic sum of potentials due to each of the charges. So if there are basically, let's say 3 charges, that is Q1, that is Q2, and the last one is minus of Q3. These two are positive charges and these two are negative charges. I have to get the potential at this particular point A. Then I'll say potential at point A is nothing but potential due to our charge 1, which will be written as kq1 by r1, and r1 is simply this distance. It is a scalar quantity, and here it is positive because charge is positive. Same way, the potential due to point charge number 2, this distance is r2, then this is nothing but kq2 by r2. And potential due to point 3 will be negative because this charge is negative, and let us say this distance is r3, then this is kq3 by r3. But here it will be negative because charge was negative. So you can simply add them, add all the potentials with their proper sign to, if you want to get the total potential. It is a scalar quantity, so there is no vector addition or subtraction. It just, you need to take care of the signs very properly. And if your charge distribution is continuous, then what to do? Then basically we assume an infinite small charge element, and that we call as dq, and it is this dq due to which we write the potential. So potential due to a small charge dq is k dq by r, and which is k is nothing but 1 upon 4 pi epsilon naught. So and then we integrate. So it is integration of all the small potentials due to those dq, and then we integrate such dq to get the electric potential due to a continuous charge distribution. Now let us do a question. So this question says that 2 point charges q and minus 2q are placed at a distance of 6a apart. Find the locus of the points in the plane of the charges where the field potential is 0. So in the plane of the charges, we need to get the locus of that particular points which are having 0 potential. So what I am doing is, I am going to take, so this is xy plane in which like there exists a charge q at the origin and there exists another charge minus 2q at the 6a comma 0. So that is the separation between them is nothing but 6a. Now let us take a random point that is x comma y. So at this point we have to take the net potential at that particular point is 0. So how do we write the potential? I'll say potential due to q is nothing but kq by r. So k, what is q? Q is q by r. What is r? R is this distance. And this distance is nothing but root over x square plus y square. What about this potential due to this particular charge minus 2q? So potential due to minus 2q is k times q. Q is minus 2q by r square. What is the distance between this charge and this charge? I am using the distance formula. So it is root over x minus 6a square plus y square. And these two charges, this is a positive potential, this is a negative potential. We simply add them with proper sign and we say the total must be 0. So their magnitude must be always equal. So I am just equating their magnitude for V to be 0. So total potential to be 0, I will simply say that it is nothing but kq by root over x square plus y square is equal to 2kq by root over x minus 6a square plus y square. So this kq and kq gets cancelled. Let us square and then cross multiply. So we get x minus 6a square plus y square is equal to 4x square plus 4y square. And when we simplify this equation, so here we get 3x square plus 3y square minus 12a x minus, one second, this will be plus 12ax minus 36a square is equal to 0. And this equation is the equation of a circle. I am further simplifying it. It is x square plus y square plus 4ax minus 12a square is equal to 0. So as we all know that this is the equation of a circle, so we will say locus will be a circle. If we want to go further and want to get the center of the circle and the radius of the circle, so what will be the center of the circle? Center of the circle is going to be minus g minus f, right? So minus, what is g? G is 4a by 2, so that is simply 2a. And what about f? There is no y term, so then f is 0. So this is going to be the center of that circle. And what about the radius? Radius is nothing but root over f square plus g square minus c. So that is going to give me 4a square plus 0 plus minus c. So here is minus of minus 12 square. So plus 12a square. And that will give me 16a square. So 4a. So radius is going to be 4a. So the locus is going to be a circle in a plane. If we are going to talking about a plane. If we are looking in 3D, then like y and z axis are symmetric. So this will form a sphere with this center and this radius. So they are just asking in the plane of the two charges. So we can say it is locus will be a circle. In 3D it is going to be a sphere.